I'm happy to welcome Jeff Clune here to CMU. He got degrees from Michigan State University and the University of Michigan. As someone who grew up in Michigan, I don't quite understand how that was allowed, but nonetheless, it happens. He went on to be a professor at the University of Wyoming, where he is now. But of course, my connection to him started in 2016, I guess, at that point.
That's right.
He joined with Geometric Intelligence, which is a startup company that Uber bought to form its AI labs. And so that's where I met Jeff. And so I've been pleased to see all the good work he's been doing at Uber. And he's, of course, going to tell us about some of his work in deep reinforcement learning and other applications where uncertainty and exploration is important. So go ahead, take it away.
Thank you. Thank you all for coming, and thank you very much to Jeff for the very nice invitation to come join you here. It's an honor to be here. So I'm going to tell you about a lot of work that we've been doing lately into kind of improving robotics and reinforcement learning with two families of algorithms that you may not have heard of before. In particular, quality diversity algorithms and open-ended algorithms. And so I hope to kind of share these algorithms with you because I think they're very exciting. But before I begin, I wanted to quickly tell you about a little bit of work that I'm not going to have time to tell you about, in case you're interested in checking it out. And the first piece of work here was actually done by my PhD student, Arash Nuruzadeh, who is here in the room with us. Arash, will you stand up? Oh, he's on the back. Here you go. It's a pleasant surprise. He just happens to live in Pittsburgh, so he's able to come join us. So this is work that we had in PNAS, which is into trying to marry deep learning with motion sensor cameras. So biologists are constantly trying to figure out how many animals are in an ecosystem, what are those animals doing, and so they want that to stop poaching and conserve endangered species, or even just to understand animals in their natural environment. And so if you pair motion sensor cameras and deep learning, you can really do a wonderful job, because those motion sensor cameras take millions of images, and so you need automated techniques to extract information from them. And Arash and our wonderful collaborators figured out how to do a wonderful job there. And in particular, we were able to automatically classify 99.3% of the images, the millions of images that these networks produce, with the same exact accuracy of humans that label these images, and then pass the rest on to experts for labeling. So that's cool. Another arc of work that I wanted to quickly mention that I'm not going to be able to tell you about today is our work into what we call AI neuroscience. So this is trying to figure out how much do deep neural nets understand about the world that they classify. And it's had this arc of papers, including the paper Deep Neural Nets Are Easily Fooled, right through plug-and-play generative networks. You might be interested in that. And then the final thing I'll say is we've also done a lot of work lately in meta-learning. So if you're interested in that subject, here are some papers, including differentiable Hebbian plasticity, which is an alternative to SGD. Differentiable neuromodulated Hebbian plasticity, or which Thomas called backpropamine, and also this brand new work which is in review at iClear called generative teacher networks, which are pretty wild and crazy and fun, so I recommend that. Okay, so now to the main event. I'm interested in telling you, as I mentioned, into these two families of algorithms that I think help with robotics and reinforcement learning. And I think that they're interesting not only for what they've already accomplished, but because they might help us solve even harder problems. And they might really help us kind of make advances in these fields. And so I want to tell you about them. And that's going to involve deep dives into our Nature paper on robots that adapt like natural animals, and our recent Go Explore algorithm that can solve Montezuma's revenge, as well as, once we get to open-ended algorithms, this new algorithm we put out called POET, and I'll tell you about them all in turn. But first, let me tell you about this paradox that we've observed, which is that in life, if you try too hard to solve something, you usually fail. But if you ignore the objective completely and you just try to explore the set of possibilities, you're often much more likely to succeed. So an example of that is this maze here. The agent at the start right here is incentivized to get to the goal. And if the reward function is distance to the goal and it tries to reduce that distance to the goal, then this optimization algorithm here will go north and bang its head against the wall forever. It's trapped on a classic local optima. But if you instead ignore the objective completely and just go out and try to find new places in this maze, then it trivially can go and find the solution to this problem. So I would actually argue that that little maze metaphor is really emblematic of many, many complicated systems, which include natural evolution and science and technology. And the idea is that if you try myopically to just optimize vis-a-vis some particular objective, and you only accept anything that makes progress versus that objective, you will fail. So for example, if you went back a couple centuries and you took this technology for heating food, and you only funded researchers who could give you a faster way to heat food, food, you would never invent the microwave, because to invent the microwave, you had to have been working on radar technology and then notice that a chocolate bar melted in your pocket. Similarly, if you had an abacus from a couple millennia ago and you said, that thing's cool, that does a lot of computation, I want more compute, and you only fund science or you take steps in technological space that give you more compute, then you will never invent the modern laptop or the modern computer, because to invent this technology, you had to have been working on electricity and vacuum tubes, which when they were initially invented had nothing to do whatsoever in terms of producing more compute. And the same is true going from this kind of energy to clean energy. You had to invest in somebody looking at basic questions in physics and space and time. So the conjecture here is that the only way to solve really, really, really hard, ambitious problems, like those in robotics, is to try to create problems as you explore the set of things that you can accomplish. And also, if you're working on one problem and you see a promising solution to another problem in your set of problems, then you goal switch and start optimizing on that new problem. You allow yourself to kind of catch chance on the wing and catch serendipitous discoveries. So we want our algorithms to do that, and I'll show you how we do that. So this notion of goal switching is really central to a lot of the techniques I'm going to tell you about today. The idea is, imagine if you have a scientist here, and this scientist wants to optimize a bipedal walking robot. If you launch the optimization algorithm and all of a sudden the robot starts crawling, instead of throwing that out as a failure, you might want to capture that moment and say, oh, that's interesting. Let's try to optimize for that objective too. Same thing for balancing on one foot. And it could be the case that this is a good idea because these might be really good stepping stones to ultimately producing a walking robot. So we call that goal switching. Oops. So one of the families of algorithms that my collaborators and I have been inventing that kind of pursue this style of search are these things called quality diversity algorithms. And so the idea is that this algorithm is going to produce a diverse set of high-performing solutions. So rather than a traditional machine learning algorithm that will give you one solution, this thing's trying to produce a set of different high-performing solutions. So there's two major algorithms in this family. I'm going to tell you about this second one, MapElites, because it was co-invented by myself and Jean-Baptiste Moret. And it's also quite simple. So the way that this works is you start with a problem that you're interested in solving. Say you want a robot that can run as fast as possible. And you also can produce you can choose dimensions of variation that you're interested in, such as the height and the weight of the robot. In this case, you're optimizing the body of a robot, just to make it an easy example. And so what you're looking for is the highest performing or the fastest moving robot in each point in this space. So I want fast robots that are tall and skinny, short and fat, and all possible combinations. So you pick these dimensions of interest, like height and weight, you discretize that space, and then you just search for the best thing at every point in this grid. So here's a run through. To initialize the algorithm, we'll take a random agent. So this could be like a random parameter vector that specifies the morphology of a robot. You evaluate it. You find its height, its weight, and its speed, which I'm coloring here via this heat map. And you put it in the proper cell. And then you just run this infinite loop where you grab something from this grid, you perturb it somehow, you reevaluate it, and you get its new properties here, and you put it in the new cell in the grid. And the key is if this cell already had an occupant, and the new thing is better vis-a-vis your reward function, then you swap it in. So it's just kind of like a parallel hill climber that's trying to find the best thing in each one of these spaces. And you loop that forever. And what's really nice about this algorithm is, as opposed to returning to you one particular solution that has an arbitrary trade-off of height and weight that you did not get to control, it returns to you this surface of what's possible in this search space. So you get this whole set of possibilities, and that allows you to learn a lot about your search space. You might find out that in this particular domain, in this cartoon, that you can do really well in the corners of the space, but you can't do well in the middle, for example, and that there's a trade-off, like this particular peak is actually the highest, but you can do almost as well over here, and you might want that for some reason. And what we'll see is that having this surface of different solutions is very advantageous. So just when we were initially kind of just figuring this algorithm out and testing it, we applied it to this soft robotics problem. So in a previous paper, we had produced this video, which shows this nice diversity of solutions to this robots that are incentivized to move as fast as possible. We gave them 4 different building blocks, which are these different colored materials. And what I was finding is, while it solved the problem, it almost was never using this dark blue bone material. And I really wanted creatures that had more bone. But another problem with the algorithm is that while I just showed you, and you can watch the video on YouTube, it's quite nice, nice. There's this long parade of different solutions. But there's a trick, and that is that we get each of those solutions from a different run of optimization. So within one run of optimization, it's almost completely converged, even though it's a population-based method, onto one style. And this is very reminiscent of a lot of deep RL. If you look at all those Mujoko walkers that have wild different movements, each one is typically taken from a totally different run that started at a different random initialization. What we don't typically have are algorithms that can fan out and explore the set of possibilities and show me all the things, all the different ways to walk that are high performing. So we ran map elites in this space, and what I wanted was variation in the percent of that dark blue bone material, as well as in the number of voxels in the creature. And then here is performance. And what you see is with classic optimization, you don't do very well. Most of the points are black, and you don't search most of the space. If you add diversity, which has been known for decades to make these things better, you get higher performing points. It's hard to see, but that's yellow there. But look how much of the space it still did not explore, even though it was incentivized to move in these particular 2 dimensions. Now, for the exact same amount of compute, same number of evaluations, this is what map elites gives you. And it's really just a sea change in terms of the diverse exploration you're doing of the space of, in this case, robot morphologies. And so you learn all sorts of stuff about this space. You find out that there are these 2 weird peaks here. You can't do very well up here. There's lots of different peaks over here. And then there's this really interesting kind of other mode here, which maybe your algorithm never would have found, because here's like a valley in the reward space that it never would have crossed to discover this totally different type of solution, which might be interesting to you for some reason. So what's also interesting is that this algorithm, map elites, often finds a better max than algorithms whose only job is to find a max high-performing solution. And that's because they get off of local optima and do a better job of searching their search space. So another nice property of map elites is that nearby solutions in this grid are by definition of similar type, at least according to those dimensions of variation. So if you pick a given solution, like right here, you have this robot that has green in the front, red in the back, and a little bit of blue here, and it's kind of like a bounding animal with a little bit of bone in its spine, and you sweep up the add more blue dimension, what you get are variations on that theme that have increasing amounts of blue. And so this starts to resemble natural organisms in the tree of life, in that you get like all the great cats, for example, but you have differences in their size or their coloration or different dimensions of variation. And we're going to harness this property that nearby solutions are similar in the paper that I'm going to show you next. So another thing I want to point out is that inside the dynamics of these algorithms, goal switching is absolutely critical. So if you take the final point at every point in that map, and you say, this is like a really good solution, for example, to that particular cell or niche, where did its parent come from? Where was the thing that we perturbed to produce that solution? Well, in this particular case, that parent was all the way over here. So to find the best thing here, you had to not be working on that problem, you had to be working on this problem, and then allow switching to happen within your algorithm. And you'll see many cases that doesn't happen, but many cases it does. So that adds a healthy dose of diversity to your search. And what's even more interesting is instead of going one step back, if you trace a final champion at one point in the map all the way back through the lineage of things that produced it, what problems was it working on over time? What you find are these really long circuitous paths through the search space. And so it would have been really hard to design that curricula ahead of time, but map elites is automatically simultaneously exploring many different overlapping curricula until something finally works, and therefore it's kind of inventing curricula and hedging its bets across different curricula. And it really shows the value of goal switching and working on many problems at once instead of only working on one problem. So we had this paper a while back called Innovation Engines, which started with the observation that nature, culture, and QD algorithms are all what we call innovation engines, which is to say that they say they have a set of things that are currently discovered. They generate permutations of those interesting things, and then if the permutations are interesting or high performing, you keep them, and then you repeat the process over and over again. And so one of the things we wanted to do is we wanted to say, could I create an algorithm that would automatically generate a lot of interesting images? This was mostly before GANs were working. But this is also, we're doing this in a very different style. Instead of having one generator that produces lots of images, here I have one little tiny network, which is interesting for reasons I don't have time to tell you about today, and it's going to produce one particular kind of image. And so you have one network producing one kind of image, and then we wanted to automatically evaluate if the image was interesting. And so to do that, we use AlexNet. And so the image that's generated has to light up one of the classes in AlexNet according to a trained AlexNet model. And what we found is that if you do that with just one class, so you have one network trying to optimize to produce an image for just one class, it performed really, really poorly. For example, here it tries to produce a water tower, and really early in optimization it locks onto this type of motif, and then it's pretty much just stuck. It just kind of adds piecewise hacks to slowly get a higher performance, which is shown here according to AlexNet, in terms of that being a water tower, but it pretty much never gets off that local optima. In contrast, if you run map elites with 1,000 classes and you allow goal switching to happen all the time, then it got initially stuck on this optima, and we actually did the counterfactual. If you run that forever, it never really gets off of that. But there was a goal switch event here. The best thing from the beacon class eventually looked enough like AlexNet to a water tower, more so than that it became the champion on the water tower class, and then was further refined by optimization to produce something that AlexNet thought was a near perfect water tower. And we see this over and over again. So you can quantitatively say single class map elites only gets a performance of this on average, whereas if you have 1,000 class map elites, you get that. And you can even just sweep across how many objectives you're going to allow. What you see is a monotonic increase in the number of goal switching that happens on average within per class, and also the final performance according to AlexNet. So it makes the optimization process easier. Now, another thing that I think is really fascinating about these algorithms is they can have what biologists call adaptive radiations. So in biology, if you have an innovation somewhere in one species, that can radiate out through the rest of the ecosystems and become kind of like an innovation that spreads. For example, in African fishes, you might have an innovation in the efficiency of metabolizing oxygen or something in the water, and that can spread out to all the different lakes in Africa and kind of become the technological platform on which further innovation is based, and then those things can specialize to their individual niches. And so you see that with Darwin's finches as well, where the initial breeding pair shows up and then radiates out into the islands and kind of produces things with different beaks and different other body types. And the same thing is true with computation. Once we invented the computer, that radiated out into all of the niches out there in the world that you see here and many, many more, and became this platform that we build on. And you want that to happen in our algorithms, and these QD algorithms allow that. So here is an example of that in this Innovation Engines paper. Early on, one of these networks produced this general motif, which is this hump on a colored background for the abaya class. And then that central innovation just radiated out into the space of other problems for other niches, and ultimately became the backdrop for a volcano, a mosque, a water tower, a beacon, a yurt, a church, a planetarium, an obelisk, and a dome. And this is literally a phylogenetic tree, just like you see in nature, where you have the initial innovation radiate out and be specialized into lots of different niches. And I think this is a really nice property to have in our search algorithms. So I want to show you now a robotics example of how we harness these ideas in combination with other algorithms to produce what we think is still state-of-the-art damage recovery in robots. And this was with my wonderful collaborators, Antoine Colli, Dinesh Terapur, and Jean-Baptiste Moret, and this was in Nature in 2015. So if we want robots to be out there in the world helping us solve, put out forest fires and help us in our homes, we're going to have to deal with the inevitable fact that these robots are going to become damaged. And if, advance, you don't want to advance. There we go, damage. So if you look to most modern-based deep RL methods or most search methods, they're really sample inefficient, as we all know. And so you could never run them on the real robot. You would just end up taking way too much time, like if you're waiting for a survivor and you're trying to find that survivor in a rubble field. But also it would probably just further break the robot as you flail around for the billion or 22 billion samples experiments that you need. And so what we wanted to do is look to nature, and we said animals do something very different when they become damaged. What they do is that they start off already having intuitions about very different ways to move before they become damaged. Then they conduct a few intelligent tests if they become damaged and pick a behavior that works despite the injury. For example, if you're off hiking in a forest and you suddenly sprain your ankle, you immediately know that your original gait doesn't work. You try that and you say, ow, that doesn't work. And you might try a different gait, like walking on your tippy toes. And you might say, ow, that still doesn't work. It's still broken. Then what you'll do is you'll leap to an entirely different family of optimization algorithms to say, maybe I'll walk on the heel of my foot. And you're like, ow, that still doesn't work. And then you'll say, okay, I'll try hopping on one foot. And you're like, oh, that's good enough. And you can hop back to your car. So think about that. You did not do what most optimization algorithms do right now, which is start with the current thing and then do very small perturbations on it and do millions and millions of experiments and slowly walk yourself to something that works. You instead started in one area of the space that didn't work, you rule it out. You went to a totally different high-performing way of walking, rule that out until you get to something that works. And so that's what we want our algorithm to do. So we have to fill each one of these bubbles right here. So to get these intuitions about different ways to move, we start off with the assumption that traditional ML is probably not going to do that for us, because if we launch it, it's going to find one type of solution, not many. And so we use these QD algorithms. In particular, we're going to use the map-elites algorithm that I just introduced to you. So the idea here is that it's going to give us a diverse set of high-performing gaits. And my clicker is being overly aggressive. So here is our robot here. It is a 6-legged robot. Each leg has 3 degrees of freedom, and it's got the sensors on board. And the way that we get intuitions about different ways to move is that ahead of time, we pick that we're going to have 6 dimensions of variation that we find that we want to see diversity in. And that is the percent of time that each of the feet touches the ground. So we have a foot sensor on the robot. That gives us a 6-dimensional hypercube here. And then what we do is we run map-elites, where you try to find a fast-performing gait for every cell in that grid. And with the result of that, which takes a lot of computation, and it is sample inefficient, but you can do it ahead of time in simulation before you ship your robots into the world, is you go from a search space that has more molecules than there are atoms in the solar system down to about 13,000 diverse high-performing gaits, which you can see all stored in this grid here according to that legend there. Okay, now I still have 13,000 gaits, so when I become damaged, I still can't search even through that search space. So then what do we do? So first I'll just show you a little bit about what it looks like inside that map. Here is one of the gaits. It uses this leg 10% of the time and the other leg, say, 50% of the time. Here's another gate. It uses this leg 10% of the time and the other leg 50% of the time, et cetera, for all possible combinations in this giant hypercube. Now, one interesting corner case is that literally in this hypercube, one of the corners was try to walk without ever touching any of your feet to the ground. And we thought that that was impossible, but we saw that square lit up, and actually the PhD student slapped himself on the forehead and thought he was going to have to rerun all the experiments because there was a bug. But we ran the tape, and it turns out, optimization, I love that one. Optimization will find a way. And so it figured out how to walk despite ever touching its feet on the ground, which is great. All right, so now we have 13,000 different high-performing gaits, but they're in simulation, and they are on the undamaged robot. So to get them onto the real damaged robot, we're going to have 2 gaps that we have to cross, if you will. So which of these gaits would you think that we should test first? Stunned silence. Who's brave enough to give us a shout out?
Pick randomly.
Pick randomly. I would argue that that wouldn't work. You have 13,000 gaits. Some of them seem to be really good. Some of them seem to be not so good. So if you pick randomly, you're probably, if you only want to do a handful of experiments, you're probably not going to get your best performing thing. Oh, that's not a guess. That's the IV person. Yeah, yes.
Pick a really good one.
Pick a really good one. That makes sense. So let me give you that. You take the best one you've got and you try it, and it doesn't work. Now what do?
Pick another really good one.
Okay, now the problem is, what do you define as another really good one? You could think, I'll just try the top n behaviors. But remember, in this map, nearby solutions are of similar type. So if this one doesn't actually work, even though you thought it did, then probably all of the behaviors nearby also don't work very well. And so you shouldn't pick those. You should probably pick something over here or something over here. And so what we're going to end up doing is use Bayesian optimization, which is really, really data efficient, to try to search through this space. And I'll show you how that works. So the prior are going to be the predictions that come from simulation on the undamaged robot. The posterior is we start conducting experiments. And after each experiment, we can update our posterior prediction for the performance of each one of those gaits as a function of what we just learned in the real world. And then we can therefore very quickly find something that still works despite the damage. And then we can have a very simple stopping criterion, which is stop if the best thing you found is about as good as you could expect given your posterior predictions in the map. And so I'll show you an example of that here. Here's a one-dimensional example. So here in 1D, what we do is in this light blue box here, step A, we run map elites and we find the best thing that you can find at every point in this search space. And then we go to the online adaptation. So the best thing that we found gives us our prior mean expectation across each of the points in this 1D space. We're also going to model the uncertainty, which is this band here, which starts off uniform. And then the dotted line here is the true performance of the damaged robot in the real world, which our algorithm doesn't know. This is just so you can play along at home. And what we do is that we try the best point. We put it on the real robot. It totally sucks. And that allows us to update. Now we know that that thing sucks. We have no uncertainty about that. And then here's where the magic happens. You not only update that point, but you update your predictions of nearby points as a function of distance in the map. Because this experiment here told us a lot about this point, and it told us almost nothing about that point. Then you go, you try your second best point after you do this, which is this point, put it on the robot, and in this cartoon example, that was good enough, and we're off to the races. So I'll show you how.
About the behavioral descriptor, the human designs the behavioral descriptor, and here the behavioral descriptor is how much you use every leg, or?
Yes, that's right. So the reviewers in Nature also asked that question. And so we did a whole bunch of experiments. And what we show is that if you pick it using domain knowledge, which we did, we knew we were going to be adapting to damage, and it's pretty good to know how to walk without using each of your legs, then you do really well. And if you pick it pretty terribly or pick it almost randomly, you still do really well, but not as well.
Right. And when you say, what would be a random behavioral descriptor, for example?
Yeah, so in this particular domain, we said, all right, what are all the things we can measure on the robot? We can measure the center of mass over time, like the torque on each one of the motors, the pitch, roll, and yaw, and we just threw all of that into some giant thing, and we randomly selected subsets of that, picked those as 6 dimensions in a map, and then searched for that. And then if it was, so that was the best we could do at being almost effectively random. So so you might say, why does it work if you're picking potentially irrelevant descriptors? And the answer to some extent is that, remember, the whole search space is more molecules than there are on the solar system. As long as you reduce it to a relatively low D space, even if you do that not very intelligently, and you pre-select all the good stuff in that space, and you're only searching in that, using Bayes opt, and having some similarity in the space, you can still basically get a lot of the lift of the algorithm. And I'll show you those plots in a second.
But this torque that you just mentioned, throughout the behavior, the torque will vary for the same behavior. Or maybe, I mean...
Yeah. So we might have done the average or something.
The utilization of a leg, for example, on expectation should be 10% for that. That could be one way.
Yeah, that's right. So we average it across the trajectory.
Some heuristics will give us this behavior description.
That's right.
That's fine.
That's right.
Okay.
And then the other thing that I would say is that we always wanted, when we first did this work, to learn it also, instead of just randomly pick it. And so it took a while, but the first author, Antoine Cully, just put out a paper last summer in which he just learns it. So you take all of your sensor data, you then throw it into PCA, you do dimensionality reduction, and then you take those dimensions, or you do an autoencoder or whatever you want, and then you take that as your space, and then you discretize that, and you search for points in that. And then what it'll do is it'll find all the good stuff. It'll extrapolate, fill in cells you never touched. It'll know the dimensions of variation that you should search along, and that also works.
Cool.
Yeah. All right. So this ends up, we all call this algorithm intelligent trial and error. It has these pieces in it, and I will show you it now. So this is a hand-coded gait. It goes 0.25 meters per second, and it goes straight on this 6-legged robot. And then now we'll drop a brick on its leg, for example, and break that leg. Sorry, robot. And then now that original gait doesn't work anymore. It's 0.03 meters per second, and it's curved. So now we launch our intelligent trial and error algorithm, which you can see here. First thing I want to do is draw your attention to this clock. This is real experiment time going on. Not including resets. And that initial gait, which we thought was our best, was actually only 0.13 meters per second, and it was really curved. So what you'll see is that we rule out by updating our posteriors. So you'll see blue start permeating the map as we start conducting more experiments. So here we're on our third experiment. And we'll see more blue flood into the map. Remember, this is a 6D map, so the blue is not only locally in the 2D space. Now here we are, I think, on maybe our 5th experiment, and only 26 seconds have passed, and we have virtually recovered the original performance of the robot, and it's walking in a straight line. And so it's effectively solved the problem, and we could call that our new behavior and move on. And what's cool is that if you look at it in slow motion, you can really appreciate the work that optimization has done here. It never ahead of time would have known exactly what the damage is going to be, but it's actually using its broken leg. It's throwing its weight around in a very dynamic way. In fact, to me, it looks like a wounded crab that somebody stepped on that's kind of limping away. In fact, most of the YouTube comments on this video are complaining that we unethically treated our robots in these experiments, which is kind of interesting. Great. So we tried it in a whole bunch of different damage conditions, 1 legs, 2 legs, etc. And in almost every case, this is the original performance. This is the hand-coded thing. This is what you run in the undamaged case. In almost every case, it way outperforms the damaged behavior. And what I love most is that it does so in 1 to 2 minutes of clock time, which is very, very rapid in terms of damage recovery. We also tried this on a totally different robot. So this is more like a factory arm sort of arm robot with many joints. We had 1 or 2 of them damaged. And again, in about 30 seconds in every case, it could deal with that. We also showed that the same technique can allow you to adapt to different environments, because there's nothing in principle different about a different environment and adapting to that as adapting to a different body. Here are some ablation studies that we did. If you run policy gradients or Bayesian optimization in the original search space, it doesn't work at all. It's too high dimensional of a search space. And all of the variants that use map elites are up here. That was like the principal component of success. And then there are subtle things you can do to boost performance even further. So recently, somebody took our exact same paper and showed that it all works with deep RL as the optimization algorithm for a policy with a deep neural net. So I thought that was really interesting to know, since that's now all the rage. So to conclude this mini deep dive on intelligent trial and error, we've showed what I still think is state-of-the-art robot damage recovery. It adapts in about 2 minutes. And what I love the most about this algorithm is that if you think about it, stochastic optimization, deep reinforcement learning, these algorithms are really sample inefficient, but they're really powerful. And what this algorithm does is it allows you to marry the sample inefficiency but the creativity of those algorithms with Bayesian optimization at game time to kind of get the best of both worlds, so you can get the creativity and the sample efficiency and the quick adaptation. So that's the end of that paper. I'm going to switch now to Go Explore, which is a new paper that we put out at the end of last year with this wonderful team of colleagues here. I want to particularly highlight Adrian and Joost, who have done a lot of the heavy lifting on this work. So this is now looking at deep reinforcement learning. And in general, in reinforcement learning, I think a grand challenge.
In the previous work, once you picked a good solution, did you fine-tune it at all in the real world? No, it's just out of the box.
That's right. It just finds something that works despite the damage. What's also cool about that is it never has to identify what the damage is. It doesn't care. So if you don't have the right sensors to figure out what your damage is, this algorithm is agnostic to that on purpose, because that's usually a huge failure mode in damage adaptation. It's just figuring out what is the exact nature of the damage. And if you sprain your ankle in the forest, you don't sit down and figure out if it's your MCL or your ACL. You just hop out of the forest back to the hospital, and this algorithm kind of does the same thing. Cool. All right, so back to deep reinforcement learning. Really big challenge in RL is intelligent exploration. We do not know how to explore domains very intelligently. And a classic benchmark there is this game of Montezuma's Revenge, because it represents one of the 2 types of hard exploration problems, which are sparse reward problems. So these are ones that give you very rare feedback. So you have to conduct hundreds of actions before you get any reward at all. And so Montezuma's Revenge is so hard for our current algorithms and represents this important class of algorithms that so much so that it's kind of become a mini grand challenge of, I think, our machine learning and deep RL research to solve this game. But there's an even harder class of problems, and that's deceptive problems. And that's when the reward signal is actively lying to you as opposed to just staying silent. So here, the reward signal is telling you to go north when you should in fact go east, and so you get trapped on that local optima. And a classic problem of that type is this game Pitfall, where you have hundreds and hundreds and hundreds of actions before you get any reward, positively, but there's all sorts of ways to get a little negative reward, like hitting this obstacle here. And so most RL algorithms literally learn to stand still and do nothing, because at least I get a 0 and not a negative score in that case, which is obviously not the global optima for this game. So classic deep RL algorithms on these games get 0 to about 2,500 points. On Montezuma's Revenge, on Pitfall, no game has ever gotten greater than 0 on this particular game. Even if you give the game emulator to a planning tree search algorithm like UCT or MCTS, they still get 0 because it's too big of a search space. And so people have turned to intrinsic motivation, including myself, to try to solve this problem. And if you look over time, most of the non-0 scores here on this is Montezuma's, was most of the non-zero scores are intrinsically motivated algorithms, which are trying to just go somewhere new. But, and they work pretty well. But 3 weeks before our paper, there was a new algorithm that scored about 10 to 11,000 and solved level 1 of this game in 1 of 10 runs, which generated a lot of excitement, and rightly so, because that was a big step up. So I think intrinsically motivated algorithms are really interesting, but the question is, why don't they do better? Like, why aren't they solving this problem? And so I thought a lot about that, and I came up with what I think are 2 pathologies in these intrinsically motivated algorithms. And the first one is exemplified by this room here. If an intrinsically motivated agent that loves to go to new places comes to a room like this, and it's never been through any of these doors, it might take this green door here, and then it might go explore that entire wing of the house, and everything is awesome and new and fun because it's never been there before. But when it's exhausted that wing of the house, what it doesn't do is come back to this room and know that it should take these other 2 doors that it didn't take. And so I call this detachment, and here's a little cartoon of it. Imagine if you have an agent here in a maze, and I'll color everywhere in the maze green that the agent hasn't been. And so it starts exploring and consuming this green, and then by chance it flips over, it starts consuming this green, and then what happens here? Now the policy's been going here for a really long time, consuming this area, and now there's no green. So we start randomly perturbing the policy. It goes here, it goes here, it goes here, it goes here, and it's not touching any green, so it has no gradient to figure out how to keep exploring. And so what I would argue is that it has detached from this promising frontier of exploration, and it doesn't remember how to get back to that. So one of our proposals in this algorithm is that we should track all of the explicit interesting stepping stones and how to get back to them so we can keep exploring. Now there's another pathology that I think exists, which is exemplified, which I call derailment. And it's exemplified by this robot, if you will, here. Imagine if you had a robot that could climb all the way up this really tall wall, and it got all the way to right there. That's very impressive. So an intrinsically motivated algorithm would say, like, hey, that was great. Let's go back there and see if we can go a little bit further to explore beyond that. But how do we do that? How do we send it back and then ask it to do something different? Well, we just perturb the parameters or the action space of this policy. And so basically we ask it to climb this wall here with a lot of noise being injected into it. And if that was a really hard thing to do, then we're just going to keep knocking it off the wall over and over and over again. And we're never going to return to this thing from which to explore. So our proposal is that we should first return to this point with no exploration added whatsoever, and then we can explore from it trivially to find out, for example, if there's a reward on top of this platform. So you might counter that will hurt the robustness of the algorithm because it's not training in the presence of lots of noise and getting really good at dealing with that, and I totally agree. But remember that we're exploring. We don't know if the reward is up here. Oh, sorry. We don't know if they're, stop it. I guess I'll have to stand closer to the USB. We don't know if where the reward, all right, it's going to keep doing that. But, all right, good. We don't know if the reward is up here or over here or over here. And so what I would argue is I don't want to get robust at this part of the wall if there's no reward up there. Instead, if the reward is here, we'll figure that out first, and then we'll practice that particular behavior over and over and over again until we solve the problem. So we divide it into 2 phases. First, we're going to solve the problem, figure out what the high reward policy is, and then we will robustify the solution in the presence of lots of noise to repeatedly get at that solution. So to initialize phase 1 of Go Explore, we just take some random actions, and everywhere we get to in the state space, we will fill up in this archive here. And then we just run an infinite loop until the problem is solved, or until we run out of time, which is that we will choose a state from the archive, right here, for example. We will return to that state. We'll go back to it with no extra exploration. That's the Go part of the name. And then we'll explore from it. That's the explore part of Go Explore. And if we find any new states, then we'll add them to the archive here. And then also, if we get back to a state we've already visited in a better way, which is a shorter trajectory or a higher performing trajectory, we'll swap that in as the preferred way to return to that cell. So this should hopefully sound familiar to you because this is an enhanced version of Map-Elites. We're finding the best way to go here and the best way to go here and the best way to go here. We're fanning out and exploring the set of ways to do everything in a high-performing way. So I like this analogy here. Intrinsic motivation, if you're searching a really big house, is kind of like shining a narrow beam flashlight in one part of the house, and then that flashlight is drawn around the house wherever it hasn't been before. So it's drawn to new areas, but it's always sending the policy to a narrow area of the space. And eventually, if it runs out of any intrinsically motivated stuff, it's just kind of detached and it doesn't know where to go. Go Explore, in contrast, is like turning the lights on in the living room of a house, and then the adjacent rooms, and then their adjacent rooms, and an ever-expanding sphere of knowledge until the entire house is fully illuminated, which I think is a more principled approach to exploration. So you can't run Go Explore in a really high-dimensional state space like Atari. There's too many states. So what we do is we need to conflate. So we have this notion of a cell representation. And all we do is that similar states should map to a similar cell, and a totally different state should map to a totally different cell. How do we do that? Well, our first attempt was we literally just downsample the image. And then it's because that's fast and it has no game-specific information. And if in the downsampled representation, two different images hash to the same downsampled thing, we call that the same cell, and if not, we call it a new cell. So when we choose which cell in the archive we're going to try to return to, we prefer cells that have recently been productive and that they led to new states, or that they're newer and that they're less tested. And when we return to a cell, we have two options. So if you're familiar with our published work, you'll only be familiar with the first bullet here, which is that we can harness the fact that simulators and video games can be made deterministic, and we can just literally replay the actions or respawn in that location. But also, we hypothesized in our initial work that you could use a goal condition policy to get back there, and I can now report that we have gotten that working. And so now we have another version that we'll publish soon, which is can deal with stochastic training if you're committed to that, which is that you use a goal condition policy to return. After you return to a cell, right now we do something really stupid, which is we just take 100 random actions, and that seems to work remarkably well. So that is all in phase one. The result of that algorithm, at least in the deterministic case, not the stochastic case, is just like a series of actions. It's not like a neural net that's robust to any noise. And if it had any noise at all, it wouldn't work or wouldn't generalize. So then we switch to phase two, which is that we give this as a demonstration to an imitation learning algorithm, which just says, oh, OK, I'll just learn to mimic that solution. And that thing then produces a policy in the form of a neural net that's very robust to noise and can solve very, very different variations of the game. So when we did all of that, here are the previous work and the previous scores. Go Explore gets 4 times more the previous state of the art, which was a dramatic improvement, including being over a human expert on the game. However, that's with no domain knowledge at all. And in my opinion, my ideal algorithm doesn't need domain knowledge, which we didn't use there, but can consume domain knowledge, especially if it's really easy to provide. So in Go Explore, that's really easy. You just tell it that cells, interestingly different situations, are those that have different XY locations, different room numbers, and different numbers of keys. And we can extract that all from pixels. So, but that's all still only used in phase one. The final policy still plays with no domain knowledge from pixels. And if you do that, then you can actually get a score of over 660,000 points on average in Montezuma's Revenge, which is kind of ridiculous. And it can solve 49 levels. But that's actually still limited by the fact that OpenAI Gym has a time limit on how long you can play the game, because they never envisioned that anything would want to play this long. So if you remove that, then our best neural net can actually score a max score of 18 million on this game, solve 1,100 plus levels, and actually beat the human world record of 1.2 million. I'm not sure what humans spent that much time playing Montezuma's Revenge, but I deeply apologize to them for stealing their record. So Go Explore now has achieved the strictest definition of superhuman performance on this task. So what's also interesting is it even beats methods that previously had done pretty well by giving demonstrations to the algorithm from humans and then use imitation learning. And that's because we could provide more demos and better demos, we think, than the human demonstration the humans were able to provide. So here's a quick video of it playing the game. I think it's really interesting because if you've ever seen videos of intrinsically motivated algorithms before, they're very twitchy because they like to try to go everywhere, and so nothing's really fluid. Whereas here we've really distilled this kind of efficient, best version of this policy that can just kind of crush the game quite efficiently. Now, if we go to Pitfall, as I mentioned, no prior algorithm had ever scored greater than 0 on this problem. Go Explore scores nearly 60,000 on average, and it's just a few thousand points of the max possible score of 112,000 on this game, and dramatically improves the state of the art on this particular really, really hard challenge. So there's a lot of really interesting future directions for this work. One of them, I just want to point out that each piece of Go Explore so far is really simple. And so that shows you that it's the problem decomposition that itself is doing the heavy lifting here. But it also creates an opportunity because you can make each one of these pieces more intelligent. So one of the things we'd like to do, for example, is instead of random exploration, we'd like to have intelligent exploration so that every time it encounters a similar situation, like jumping a log or swinging over a pond, or in my case as a child in Michigan, climbing fences, once you have that skill, you can explore so much more of the world, and so you can reuse that skill to more quickly explore the world. We're interested in working very hard on learned representations instead of engineered or random representations, and you can use lots of different methods to get those. We're showing that, and working on trying to get this working on a really hard robotics problem, because a lot of robotics problems are really sparse. You want to give it high-level goals, like, hey, robot, clean my kitchen, or find survivors, and then you want it to just go figure out how to do that and work in the real world. So you could imagine a pipeline like this. You solve it in a simulator, maybe a deterministic one, you robustify it in a stochastic simulator, then you transfer it to reality, either using like the techniques I just described in our Nature paper, or maybe domain randomization, like OpenAI did with the Rubik's Cube, and then optionally you could learn more in the world if you want to. Here is some more unpublished work where a robot is solving a very, very, very difficult sparse reward problem where it doesn't get a reward until it kind of puts its toys away, something I wish my children would learn to do. And it's able to figure that out in this situation only by getting a reward once it does so. So to conclude this mini deep dive into Go Explore, we've introduced a new type of algorithm for hard exploration problems. I think it opens a lot of exciting research directions in moving the needle on really hard exploration problems in robotics and reinforcement learning. But also, in the theme of this talk, I think it shows the value of quality diversity, that having this set of diverse solutions is really, again, powerful at solving a previously unsolvable problem. So what's missing? I've been telling you that QD algorithms are awesome. They can produce a diverse set of high-performing agents. They take advantage of goal switching. They conduct divergent search to find out what's possible. But ultimately, their ability to innovate is still constrained to the environment that they're running in, right? They're still trapped in that one problem. So no matter how long you run one of these things, it's only going to give you like a really good Montezuma's revenge-playing agent. It's never going to cook me dinner or clean my, or invent a new form of calculus, for example. And to some extent, that's because that's what traditional ML does. We run our algorithms within one problem domain, and no matter how long you run any of these algorithms, they'll only give you a really good Dota-playing agent, and they'll never give you something different. So we're motivated by what we call open-ended algorithms, and these are algorithms that can just run forever and endlessly innovate. And so if you think about it, an example is natural evolution, another example is human culture. So natural evolution on its own with no objective ended up producing jaguars, hawks, and the human brain, and all of these other creatures, and it's still going. Think about that. Life on this earth has been going for 3 billion years, and it is still innovating. Could anyone in this room write a piece of computer code that would be interesting to come back and check on 3 billion years later, no matter how much compute you give it? The answer is no. But there's no reason that we shouldn't be able to write algorithms that do that. I mean, Darwinian evolution is a remarkably unintelligent algorithm. We should be able to beat that, let alone match it. So I think it's a really cool grand challenge to think about as a research community, is how do you write algorithms that do that endlessly innovate and solve problems? And so one of the things that I think is really essential is that algorithms have to invent their own challenges and solve them and harness goal switching, which is in line with the themes that we've been talking about. So natural evolution invented the challenge of leaves way up in the tree, and then also invented the solution to that challenge in the form of caterpillars and giraffes that can go eat those leaves. And then those things become new challenges for birds and for lions to go hunt in a never-ending, open-ended innovation engine. So our first attempt to, or our most recent attempt, I should say, to try to create one of these open-ended algorithms is this POET algorithm with this wonderful set of collaborators. And I really want to highlight Ray Wang, who's done a fantastic job here. And so POET stands for the Paired Open-Ended Trailblazer. And the idea here is that we're going to periodically generate new learning environments. So we're going to have a parameter vector that specifies an environment, and we're going to directly search for different kinds of environments. So different parameter vectors lead to different environments, and we'll start searching for for them. And we'll have a population of these environments, and each environment will have an agent that's sitting in it that's optimizing, trying to solve it. And what we'll do is we'll periodically generate new environments, but we'll only keep them if they're not too easy and not too hard for the current population of agents. And then we'll start optimizing the agents to solve those newly generated problems and the old problems. And we'll allow goal switching in between. So I'll show you how that works. The domain is this obstacle course here, and you have this little agent that is trying to go as fast as possible, and here are the degrees of freedom that we allow the environment to vary in. So the way that it works, you start with this parameter vector phi that specifies this easy environment. You start optimizing a different parameter vector theta that controls a deep neural network that is trying to solve this problem. They optimize for a while. Eventually theta is good enough on that problem, so we'll generate a new perturb parameter vector that specifies a different environment, and we'll seed with transfer learning. This agent goes into this environment, so it gets a head start. And then we'll try to generate a new environment. Maybe that's too hard for either of these agents, so we'll throw it out, generate a new environment. Here it turns out this is the right stepping stone. We'll transfer that in. This doesn't have to be linear. We'll take this environment, we'll generate this, and then we'll we'll test all of these in here. We'll transfer the best one in, which happens to be that one, and now it starts optimizing there. And remember, we're also still optimizing this on this and this on this. All of this is happening simultaneously, and it eventually kind of gets this expanding set of challenges and solutions. Now, mention you eventually generate this really hard problem here, and initially it looks like theta 6, which came from theta 5, is the best stepping stone. But it gets stuck in a local optima, and so you keep optimizing, and eventually theta 4 comes up with an innovation that makes it goal switch into that environment and become the new champion there, and then more optimizing on that problem actually produces a better solution here, and now we got off of this local optima, and we got a better solution to this environment via goal switching. So under the hood, there's a 3-layer neural net optimized with evolution strategies, but you could use any RL algorithm you like. So here's a little video of a fun robot. All of the environments you're seeing here are automatically generated by the algorithm. And what you'll see is that early on in optimization, the algorithm is generating very simple environments that the agent has to learn to solve. And it's also doing kind of each dimension of the difficulty separately. So first little stumps, then little gaps, then a little bit of ruggedness in the terrain. Later on, optimization and the algorithm starts producing harder versions, but still kind of each single dimension separately. So taller gaps or bigger stumps, etc. And this thing eventually learns to solve them. And then finally, the algorithm starts automatically combining these different degrees of difficulty together. So you get big gaps and big stumps and rugged terrain all together. And this thing is still able to figure out how to solve this obstacle course. Now, here's another fun one that it created. We didn't even think of that it could do that, and then invented it and solved it. So we kind of manually set these into different levels of difficulty according to some rules that we came up with so we could get this extremely challenging class. And that allowed us to do some quantitative studies. In particular, if you take the very, very difficult environments that Poet generates and gets this performance, and then you directly drop a new neural net and you directly optimize it on that problem, it never works. And that's because there's no curriculum whatsoever. So you might say, that's not fair. You should give it a curriculum. Here's a fun video of it failing in each one of these cases. Oops, that didn't work. I'll skip that video. But anyway, you might say, that's not fair. Let's give it a better curriculum. So you go through, you take some hard problems like these, and then what we do is we take the parameter vector that specifies that environment and the parameter vector that specifies that environment, and we create a kind of a linear interpolation along these degrees, and then you just create some environments along the way, and then you start optimizing here, then here, then here, then here, then here. You'd think that gives you a nice direct curriculum to that target, but you'd be wrong. That never works. In every single case we tried, at some point along this curriculum, optimization can't solve this problem from this problem because this isn't the right stepping stone for that problem. You need that kind of non-intuitive goal switching that you get from QD algorithms to give you the right curriculum to each one of these really hard problems. And so the harder the problem, the further back in the chain the system broke down and wasn't able to solve it. You need all of that goal switching. So here's an example that I think is really nice. Just in the initial super simple flat environment, we start optimizing a neural net, and it produces this walking behavior. And notice that it's dragging its knee here for whatever reason. So then Poet creates a new version of this environment, has little stumps. That knee dragging behavior no longer works, so it learns to stand up. That ultimately gives it a much better performance in this domain. Now Poet is automatically checking for goal switching, so it says, let's see if this works in this this environment, lo and behold, that's actually a better way to go and solve that original problem. So it stands up and it's faster. And then with further optimization in this environment, it gets an even faster score of 350. Now we went and did the counterfactual. If you run this thing forever in this problem, you still get a knee-dragging thing that never ends up doing as well because it's just stuck on that local optima and you needed goal switching. And I also think this underscores how difficult it is to design curricula by hand. How many of you would have thought that to solve this simple problem, what you should do is create a harder problem, have it work on that for a while, and then come back, and it will ultimately do better. So again, quality, diversity, open-ended algorithms, they're kind of hedging their bets. They're simultaneously trying out multiple curricula and then just keeping whatever works, which I like.
So, to ask you something, if we start from a very hard environment,
yep.
will we learn anything, or we really need to start from easy and then go?
Yeah, so that is actually this experiment here. If you start directly in the hard environments, you get no performance at all because there's no curriculum. So the only way to solve these hard problems that we know of is to do POET. Okay. So I'm going to try to, I'm almost done here. Let's skip beyond that. So you do need POET to solve, you need goal switching. If we run POET without goal switching, you never solve these very, very difficult problems here. So I think there's a lot of interesting future work for this direction of research. One thing is just to put it into more complicated environments. So here's a 3D environment instead of a little 2D environment. I'd love to see POET here. You could also put it into multi-agent setups and like let it do kind of the equivalent of self-play, but in a variety of different environments, which would be really cool. But I think what really fuels my intuition is to say, what if you put it into an environment like this? Right? Like compute is speeding up exponentially. Moore's law will help us. What would POET do if it's in a world this complicated where it could have to barter with other agents to buy goods and armor, cooperate with agents, compete with them, fight with them, climb buildings, deal with aerial predators, who knows? How many robotic skills get learned once you have the compute to let an algorithm like POET rip in this sort of a space? I think that's really interesting. So you could also optimize the body as well as the agent itself, which if you're interested in robot design, that might be very important. So one final thing I'll point out about POET before I'll conclude the talk is that I think it's also got a lot of promise for meta-learning. So in meta-learning, you need a big distribution of tasks to train on. POET can automatically generate that distribution of tasks for you, so you're not designing it yourself. That allows you to get things that know how to learn and quickly adapt to any arbitrary new environment. There's two different ways to do that. You could either take all your POET tasks and put them in one giant distribution, or you could have each environment in POET be its own distribution that narrowly is focusing on a subset of the world, like water worlds and canopy worlds, et cetera, et cetera. And so I think there's a lot of really good work to be done there. This is all very similar to OpenAI's new robotics cube thing, where they're automatically generating test environments and meta-learning a solution to them. And they point out a lot of the connections to this work in their wonderful work. So we're all on the same page there. So here's my conclusion slide. I think that quality, diversity, and open-ended algorithms have a lot that they might offer to the research community in terms of moving the needle on robotics and deep RL. I think they create and collect stepping stones, which is really interesting. They harness goal switching to avoid local optima and capture serendipity within the algorithm. They benefit from adaptive radiations. They invent their own curricula by hedging bets with multiple overlapping curricula and then choosing one that works. And we see time and time again that developing this curricula is counterintuitive, which is why we should automatically try to learn them. I think they're really also interesting because they capture a lot of the open-endedness of natural evolution and cultural evolution in terms that they potentially could endlessly innovate if we could give them the right domains and maybe pair them with, say, architecture search. And I think that they therefore may be the only way to solve really, really ambitious problems that we set for ourselves in the community and kind of discover the full gamut of what's possible out there in our search spaces. And so I just think it's really interesting to think about algorithms that kind of endlessly generate and level up robotic skills and agent skills, etc. So with that, I'd like to say thank you to my main collaborators, without which I couldn't have done any of this work, as well as all of you for listening.
Okay, great. We've got time for questions.
I'll start with the hardest one. Get it out of the way.
So, the big problem with AI systems is the more you know, the slower and stupider you get.
That sounds like my life.
Well, I'm concerned that it would also happen with your system in that the more you cache good things,
Yes.
the harder it is to find the right good things and to find them quickly.
I think okay, I thought you were actually going to ask a different question.
Go ahead and ask it.
Well, I like that question, but I will pop my own question on the stack, answer it, and then I'll come back to yours. I thought what you were going to ask is, which I think is related to what you asked, in Poet, for example, as you start to expand more and more types of environments, then you can't do all possible pairwise comparisons to see what should switch to what as you grow, right? That's not going to work. But you don't have to do that. You could always just have some sort of a rule that says transfer to nearby stuff, and transfer with a probability of distance in the environment space. And so most of the time, water world creatures are transferring to water world niches, and only rarely are we flopping them up on the beach to see if they can crawl up onto a sand world or a beach. But every once in a while, we should do that. And you might say, where do you get that distance function? There's a variety of ways you could do that, but one of them is just the phylogenetic tree. You could just use the tree distance to know what's related to what. And so that allows you to dramatically reduce the space of the pairwise comparisons. So I'll pop that off the stack and go back to your question, which is more broad, which is all of these algorithms that are collecting interestingly good stuff, do they kind of grind to a halt? Well, I mean, you could imagine just raising the bar for what you consider to be high quality, just because you have to. In an ideal world, you wouldn't have to, but you could imagine doing that. And you could therefore kind of thin the space. So initially I have a dense concentration of interesting stuff here. As I fan out, I can't maintain that level of density everywhere, and so I'll just have fewer of those, but in exchange I'll have stuff way out here in this space, and you have to deal with that. What do you think?
It is, the polite way to say it is an empirical question as to whether that will work.
Yeah, that's fair. I also think that Moore's law will keep giving us better computers, and so the stuff that seems impossible now will seem routine soon. And so deep learning never would have worked 15 years ago, and here we are with it working all the time. So I think this is the kind of algorithm that we can start to get work on. We can do work now, but we're probably doing what people did 10 to 15 years ago in deep learning, which is that we're creating the algorithms and exploring the space such that we're ready to pounce once the computer is really ready to have these algorithms truly shine. And I do think that to really, to show that, like that video game world I showed you, you're going to need a lot more compute to do that. I don't think you can just get away with better algorithms, but it's going to be both. Another thing that I'll mention is that if we can abstract the key ingredients that really make these open-ended algorithms work well, we might be able to shave many, many orders of magnitude off of the search. So we don't need a planet-sized computer to reproduce the magic that happened on Earth. That's kind of the bet. So like Josh and I, Josh Tenenbaum kind of like to debate. He's like, yeah, if you give me a planet-sized computer, of course you're right. The question is whether or not you can do it without a planet-sized computer, to which I say, game on, let's get to work. Yeah.
So in your in the beginning of the talk, the co-explore beginning, you were using pixels directly for your policy, right? In critic, but then you showed this unpublished work about putting some objects inside a drawer, and
Yeah.
you said here we're using ground truth state information.
True.
And then at the very end you showed this nice three-dimensional ancient Greek type of video game.
Yeah.
And the question is, what about the perception part, the state estimation part? In the first 2D game, Montezuma's Revenge, this don't say it well, but there you didn't need state. You used it like saying, okay, which is the room and what is the XY location, right?
Yeah.
So essentially the only job that perception needs to do there is destabilize your video and figure out how far you moved and so on, right?
Yep.
But then as you go to the 3D world and it's harder, when you say ground truth state, in that work under submission, you mean XY, 3D locations of objects and where the drawer is and so on? Is this what you mean?
Yep. Like the angles of all the joints of the robot, where the blocks are, the ground truth locations. But we are working on pixels. I don't think in principle there's any reason that it won't work from pixels. It's just harder. But to answer the highest level question, yes, conflation is hard. It's one of the central challenges of artificial intelligence, is to how do you intelligently conflate from high D to low D. I think that humans, when we explore the world, we know what counts as interestingly new. And that is just a ripe and interesting and difficult question. If you ask me to explore this building, I know that one of the things I should do is go to different X, Y, Z locations, but I also know it might be interesting to kind of open a cupboard or look in a trash can, and that's interestingly different than standing here and watching clouds go by, which changes my percepts, but doesn't do it in a way that's useful or interesting vis-a-vis exploring the building. And so that's why I had a slide up there saying that I'm really interested in learned representations. So I think agents have to explore the world, get some sort of a representation of everything that they've seen so far, and then figure out kind of what counts as interesting versus not in that space. So let me give you an example of how that might work. You could imagine that in Montezuma's Revenge or in a three-dimensional space, you run it initially with a random representation. So you take a random neural net, you take its latent, its hidden code, you discretize that, and those become the cell representation for Go Explore, and you try to find, you get to as many places in that space as possible. And then that maybe gets you to solve, say, half of the level 1 of Montezuma's Revenge, or a level and a half. Now I've gathered a lot of interesting information about the world, everywhere that I can go in that first level and a half, as well as some reward information. Keys matter, doors matter, maybe moving around the world seems to like matter vis-a-vis the value function of the RL agent. So now I could train like a value function, then take its latent embedding and discretize that and repeat the process and run Go Explore in that latent code. Maybe that gets me to solve 2 or 3 levels of Montezuma's, and I can iterate this process over and over again. So just like a human within its life kind of learns what counts as interestingly new, these algorithms should be able to learn what counts as interestingly new. Now that said, this is like ongoing research and it's very hard, but I think if we crack that, then it should work in 3D, in 2D, in even some other domain like genomic sequences or protein folding or something we don't even really know how to create a good domain representation for.
Right, though it seems that for that super hard game, you went huge way just by knowing X, Y,
Yep.
room, and key.
Well, that's why I think it's actually, and this is true for even also the intelligent trial and error, it's usually really easy as a human scientist to inject that kind of domain knowledge. We know roughly that in protein folding, what you probably want is like different amounts of like surface area and contact forces, and that in exploring a building, go to different XYZ locations. Like imagine if you set a robot to explore Carnegie Mellon's campus, and you only said get to new XYZ locations. So you gave it that domain knowledge. What would it do? It would like learn to open doors, walk down hallways, climb stairs, take escalators, climb trees, climb flagpoles, climb the Tower of Learning, et cetera, et cetera. It would gain all these skills just motivated by that little bit of domain knowledge. And so usually I don't think it's that hard to provide that, but I still think it's interesting to see if it can figure it out for itself, which is ultimately where we want to go.
And in all your talk, you didn't use demonstrations anywhere, right? Was just a single agent doing.
That's right. And what's cool about Go Explore is that it generates the demonstrations for you. So in any...
Sometimes, like for example, me, I would potentially, when you're little, you will never learn to tie shoes unless somebody shows how to tie shoes. So I'm pretty sure at some point we can look at somebody else to...
Sure.
At somebody else's trajectory, let's say it this way.
It speeds up learning a lot, but I bet you if you ran Go Explore in a tie shoeing simulator, it would figure out how to tie its shoes. It would just take a while. And so if you want to be fast, you should definitely learn those demonstrations, and we want our AI agents to be sample efficient. But I do think it would discover, I mean, somebody had to figure out the first, whatever you call that knot, bow tie knot? What is that? Yes.
You have other questions?
Oh, I thought you had a question. Sorry. Yes.
Just asking, the goal condition policies which you mentioned,
Yeah.
are you getting something better than 18 million on that?
No. It's definitely, well, actually, there the issue is that we run out of memory. I think if you ran it, if you had infinite memory, it probably would ultimately get there. We haven't yet figured out a version that you basically stop giving it goals and you just let it run. Because in that case, you're always giving it the next goal that it's like learning to do. So it's a slow process. It doesn't have what this algorithm has, which is it can kind of generally learn how to play the game, and then it can just generalize to all sorts of new situations. So no. But I think we could get there if we cared. But at some point, I don't care about beating Montezuma's Revenge anymore. Yeah.
Hi, thank you. It's a great talk.
Oh, thank you.
Learned a lot. I have a high-level question, not technical, but from a perspective of a PhD student. I would like to know, when you first have map elites, did you already form the idea of the robot damage recovery? Which comes first, and how do you get your way there?
Yeah, and the answer is no. So we've just been interested for a long time in terms of, this is Jean-Baptiste Moret as well, and Ken Stanley and Joel Lehman, in terms of how do you get, it's actually motivated a little bit by open-ended algorithms and intelligent exploration. How do you kind of get an expanding set of diverse yet high-quality things? And before Map Elites, what happens is you would encourage things to be different than what came before, but they would tend to cycle or chase around the space, like go in one direction, but not kind of have this property of fanning out. And so we basically said, well, maybe we should just kind of discretize the space and think of local competition. So one of the really cool insights behind Map Elites is that everything is only competing on vis-a-vis the overall performance objective inside of that cell. So for example, if you want the fastest ant and you want the fastest cheetah, then you can never compare them on speed, because no matter what weighted combination you have of diversity and performance, the cheetah is just going to crush that ant. But in Map Elites, you never compete the cheetah with the ant, because you, instead of doing global competition, having everybody compete on this one objective, you only compete with things that are like you, according to the dimensions of variation. And so this was actually an insight by Joel and Ken in their original QD algorithm, which is that if competition is local, then I can get the fastest ant and the fastest cheetah and the fastest bear, and neither of them precludes the other. And so that was like an insight just pushing on this direction of how do we get diverse, high-quality stuff, and that led to Map Elites. And then Jean-Baptiste realized that you could really harness that repertoire to do Bayesian optimization, to do rapid damage recovery. And there's lots of other papers since then that have taken the repertoire that is produced by these QD algorithms and does all sorts of really nice things with them. So I actually maybe encourage this room, like what would you do if you had a diverse set of high-performing things that you wouldn't do if you didn't have a full set? Like a repertoire is a really interesting thing from which you can create a lot of different algorithms. These are just a few of the demonstrations of that idea.
So it sounds like your advice to PhD students is they should run their own Go Explore algorithm.
That's right.
Invent lots of cool algorithms, don't worry about what they solve, and later when you're a professor, you'll discover one of them does something truly amazing.
Yes. I totally agree with that philosophy.
I think with that, we're going to wrap up. Let's thank Jeff one more time.
Thank you.